So here's a game plan for what's going to happen here on. So today is November 29. So November 29 and December 1, you are all going to be standing here and making presentations, one person from every team. And you should send me your files latest by tomorrow night so I can have them on my computer. So November 29, today we will study chemical equilibrium. We will talk about chemical reactions and how do we use Gibbs free energy to think about how do chemical reactions really reach equilibrium and what goes on. It's going to be quite easy if you understand chemical potential. And this will also continue on December 3. We will again talk about chemical equilibrium. And after that, we have December 6 and December 8. I will be talking about kinetics. This part is not on exam. If you do not want to come to class, you don't have to come to class. There won't be a pop quiz starting December 6 on December 8. This part will not be on exam. If one of you shows up, I'm still going to teach. I really hope as many of you show up. It's most 481 classes don't go over kinetics at all. It becomes the orphan child of PChem, which is really bad and we ignore it, but I want to give you a flavor for it. These lectures will be fun. We will talk about things called Fick's law and how much time do reactions take to happen. We will set up the machinery for it, so we'll be ready for it, but it will not be on exam. And then December 10 will be a recap of the whole semester. We will go over the main concepts. It's hard to recap everything in 40 minutes, but it's not really for your exam. If you understand the key concepts, the exam will not be too hard. Okay, and the exam will be take home. You will get around 5 days to do it. It will be released after December 10, 3-4 days after December 10, it will be take home. I will set up how to submit it. There won't be class, it will be Google form, it will be open book, open internet. So these 3 classes, you can skip completely if you want. If you want to go on a holiday to Hawaii or somewhere, you can do that. Yeah, but try to come. Kinetics is cool, it's fun. Any questions? Go ahead. What? Oh yeah, but keep it hush. Yeah. No, there won't be a last homework. There will be last homework. So there will be some questions from this topic on the exam. There will be some practice problems on this topic, but I'm not going to give a homework. I want you to form a big picture of the whole semester. Use this time to think about chemical equilibrium is nothing but an application of chemical potential. So it's okay. Any more questions?
You said it's not in class.
There won't be a class, so if you come.
Right.
So there will be a Google form or something where you can upload it. So you will have, if you write it on a paper, you will have to scan it and do that. Okay, that's not too bad. Okay, great. That probably made you all happy, right?
Yeah.
Yeah. In-class exams suck. I don't like them. I would do quite bad at them, honestly. So I feel like I'm being unfair to you if I give them in class. Okay, so let's talk about. Okay, there will be a question from the coming next classes, so pay attention. And there is no homework, so you won't even know where you screw up. Okay, so pay attention. So we are going to talk about chemical reactions when A, let's say 2A plus 3B is changing to C plus D, or more simply, A is changing to B. And we want to study which direction a chemical reaction takes place in. And when equilibrium is attained, do we have only A? Do we have only B? Do we have a combination of A and B? And furthermore, can we change pressure and temperature to influence more of A or more of B can form? And that's what we are going to study in the next 2 classes. In order to do that, we need to do a bit of a recap about chemical potential. Okay, so the reason I say chemical equilibrium is just an application of what you have done so far is because that's what it really is. If you don't understand chemical potential, the remaining part will be confusing. If you understand it, it's going to be super easy. So in order to talk about chemical potential, let's start with, anytime you hear chemical potential, you have to remember it was defined in a bunch of different ways, right? It was the partial molar of G with respect to some things, keeping some other things constant. It was also partial molar of A with respect to something, keeping some other things constant. And what you differentiate with and what you keep constant changes, right? Whether you have G or A or H. But chemical potential had a very special relation with G, right? It didn't have this special relation with A, it had it with G. It is the Gibbs free energy per mole for a single component system. It is not the Helmholtz energy per mole. It is the Gibbs free energy per mole. So in order to talk about chemical potential, we will start with the fundamental equation for Gibbs energy, which is dG is equal to VdP minus SD. And remember, we said that this means that partial G by partial P at constant T is equal to V. And for this, we showed that for an ideal gas, this means mu is equal to mu naught. I'll write not on the top, plus RT ln P by P naught. If this relation is Greek to you, that's bad news. The final exam is going to suck. Okay, make sure the couple of lines that go into deriving this relation are, you look at the relation and you know exactly where it came from. It came by using the ideal gas law and differentiating this, okay? In fact, going from this relation to this relation should be obvious to you. If not, you need to do a bit more work before you get comfortable for the final. So we have this. Now, normally, we can set P naught is equal to 1 atmosphere and mu naught is equal to chemical potential at 1 atmosphere. So that gives us mu is equal to mu naught plus RT ln P. This is true only for an ideal gas. Here we said, well, for a non-ideal gas, it will look something like RT ln fugacity. Remember, we had that relation. So that was only for a pure component. Now we are ready to talk about mixtures. If you have a mixture of gases, and possibly even liquids, if you have a solution, if you have a mixture of many things mixed together in different phases, we can write down the same relation, assuming ideal behavior, okay? We have a mixture of gases and we assume ideal behavior. Then what this is going to look like, this will just be mu A. Instead of mu, we will have mu A, right? Is equal to mu naught A plus RT ln partial pressure of A. What do we know about partial pressure in an ideal gas? Dalton's law, way before 481. Why do you have a tie on? Oh, good luck. I thought it's like your New Year resolution or something. Wear a tie. Okay, so for an ideal gas, PA is equal to XA times pressure. Okay, this really goes back to lecture 2 or 3. For any gas, PA plus PB is equal to pressure. The sum of partial pressures is equal to the total pressure for any gas. However, the partial pressure equal mole fraction time the total pressure only for an ideal gas. And the key idea here is that for an ideal gas, the gases really don't have they don't care what else is there, right? They just look at the number of particles you have. So if you use, so let's call this equation 1, let's call this equation 2, let's call this equation 3. If you use 3 into, you get mu A is equal to mu A naught plus RT ln XA P, right? And again, remember, this is only for an ideal gas. We are way inside ideal gas territory. We have made ideal gas assumption a couple of times now, right? On top of this, if you make one final assumption that the thing is happening at constant temperature and pressure, net pressure is equal to constant. What do I mean by this? I mean, you have a chemical reaction happening possibly where things are changing. A is changing into B, B is changing into C, everything is going on. But the chemical reaction, for example, is happening in some open beaker, okay? And this beaker is given heat or whatever is going on, but the whole thing is kept at a constant temperature. And most importantly, it's open to the atmosphere. It's at a constant pressure. You have a question, Stella? P net. So the point being here is that PA plus PB is equal to constant. Overall, they are constant. The net pressure is constant, but the things are changing themselves, okay? So if net pressure is constant, then in this equation number 4, worrying about P is pointless, right? It is some constant. Maybe it is 1 atmosphere. It can be taken out once again. So mu A is equal to mu A naught plus RT ln XA plus RT ln P. And if P is equal to constant, and the thing here is this is the total pressure. Let's say it is, oh, sorry. Let's say this is equal to 1 atmosphere, the total pressure. In that case, what is log of P? 0, right? Does the base matter? No, log of 1 is 0 to any base, right? So in that case, we get mu A is equal to mu A naught plus RT ln XA. And this I'm going to call equation number 5. So the key equations that I want you to remember today, which we have seen in the past, is mu is equal to mu naught plus RT ln P for a pure gas, and mu A is equal to mu A naught plus RT ln XA for a mixture of gases or even liquids, however, assuming ideal behavior. If it's not ideal, it's not going to be true. Okay, we are going to use this in our study of chemical equilibrium. Okay, I'm going to turn the page. So I will write down the equation again. We showed that mu A is equal to mu A naught plus RT ln XA for ideal mixture. Similarly, if you had B, you're going to have mu B is equal to mu B naught plus RT ln XP. You could have as many components as you wish. But clearly, most mixtures are not ideal, right? Things don't interact as ideal gases. In reality, barely anything is ideal. Maybe argon or krypton or xenon, these things are ideal, but even they show complicated behavior. So in reality, this equation is not going to be true. So for real mixture, so if you were able to measure mu B and subtract out mu B naught from it and divide by RT, you should get log of something, right? If it's an ideal mixture, what should I put over here? Mole fraction, right? XB. If it is a not ideal mixture, it won't be mole fraction. And whatever this thing is, we call it activity, denoted with a small letter A. So A is called activity. For ideal behavior, activity A is equal to mole fraction. So A activity of B is equal to mole fraction of B, activity of A is equal to mole fraction of A, so on and so forth. But in general, it's going to be something different. So I mentioned to you early on that in thermodynamics, a lot of these, some quantity is equal to a reference value plus temperature multiplied by log of something. This type of behavior is typically derived for ideal behavior, but people like it so much that they really want to use it, and they introduce new terms so that they can still use those relations. And that's where real life thermodynamics becomes very complicated. The last time we saw this, it was fugacity, right? It's like, what is this fugacity? Where did it come from? It's just a desperate attempt to use that log relation. That's exactly what we have over here. And you can also define the activity. So we said that it is going to be mole fraction for ideal behavior, right? So if it's not ideal behavior, it's going to be mole fraction multiplied by something else. And this thing is called activity coefficient. A lot of real world thermodynamics for polymers, for batteries, for geology, for material science is about measuring these activity coefficients as a function of concentration. If you can measure these activity coefficients as a function of concentration, you can go and use this relation and talk about phase diagrams, whatever you want to talk. As we will see soon, we will talk about equilibrium constant. So therefore, in most general case, we numbered this as equation 5, right? This was equation 5. So equation 5 becomes mu B is equal to mu B naught plus RT ln activity of B. This equation is true for absolutely anything. It doesn't have to be ideal. The reason why it's true for absolutely anything, because it is almost like doing this. We have defined activity as the thing that makes this equation true, right? So it's almost cheating, but it's very useful. Any questions about this? So to recap, we have seen three equations for mu. For a pure ideal gas, mu is equal to mu naught plus RT log of pressure, okay? For a mixture of gases or liquids, instead of mu is equal to mu naught plus RT log P, we have mu A is equal to mu A naught plus RT log mole fraction, again, assuming ideal behavior. However, if it's not ideal behavior, instead of mole fraction, we use activity and we get relations such as mu A is equal to mu A naught plus RT ln activity of A. And activity is related to the mole fraction through the activity coefficient. So the activity coefficient can be less than 1, it can be more than 1. If it is equal to 1, we have ideal behavior. Any questions about this? Okay, so hopefully this brought you back from the holidays. We saw some active chemical potentials, and now we are ready to start talking about chemical reactions. We are going to use these relations. Let me number the pages. So even though I said that 6 and 8 are going to be kinetics, there is a small but non-zero chance that I'm unable to finish equilibrium on December 3. If that happens, I will use some of December 6 to study equilibrium, okay? And then start with kinetics. Is that fair? Because I don't want to rush on December 3, right? If it looks like, oh, I cannot finish it, which means that, so basically anything related to chemical equilibrium is on the exam. Chemical kinetics is not on the exam. If this means that I have to do some of chemical equilibrium on December 6, it's still on the exam. So if you are planning to skip December 6 because you don't care for kinetics, because you don't care for time, then you better make sure. So let's talk about chemical reactions now, which, if you understand these three chemical potential relations, is not going to be too complicated. So we have some chemical reaction, let's say A existing in equilibrium with B. And we know that at constant temperature and pressure, the condition for spontaneity, as very nicely summarized in a meme by Ryan on the Slack channel, is dG at constant temperature and pressure should become negative, right? So this means that if GB is lower than GA, which reaction should be favored, forward or backward? Go ahead, huh? Forward, because the free energy gets lowered when A changes into B, right? If GB is lower than A, forward reaction is favored. If GA is lower than GB, backward reaction is favored. And when GA becomes equal to GB, we get chemical equilibrium. And that's when things exist together, right? And chemistry is really study about chemical equilibrium, right? How things reach equilibrium, what is the concentration we have. If you think about the pH, or things like that, it's all related to chemical equilibrium, right? So, and you have seen this in pre-phys chem, in Gen Chem and other classes, you have seen this. Now we will look at it on the basis of your superior knowledge of chemical potential and things like that. So let's think about a chemical reaction in an abstract way, okay? Let's think about a chemical reaction in an abstract way where we define a progress variable to account for how much of the chemical reaction has progressed. And we denote it by, does anyone know what to pronounce this? Z or something, right? We call it squiggly. So it's psi or squiggly, whatever you want to call it. Everyone's confused about Greek letters now, right? With the new and Omicron. If you've watched Futurama, then you know Omicron, you're very well familiar with it. So we have this squiggly, which denotes the progress of the chemical reaction, which means that d psi moles of A convert to d psi moles of B. I'm using this notation because Atkins uses it. So if you go and read it, I want you to be consistent with it. I would have used some other notation. That's fine. So it's a progress variable which tells us how many moles, how much has the reaction happened. So when the psi is 0, you means it's all A, you have found no B. When psi is 1, it's all B and there is no A left. So when d psi moles of A convert to d psi moles of B, and remember, we are going to study all of this at constant temperature and pressure. Next class, we will talk about what happens when you change pressure or you change temperature, but the setup today is constant temperature and pressure. So in this case, and let's say total moles do we need total moles? No, we don't need total moles. Don't say anything about total moles. So in this case, what is dg? If d psi moles of A have converted to d psi moles of B, can we write down dg? Any ideas? It's constant pressure and temperature. So let's start with the basic equation. dg is equal to vdp minus sdt plus mu A dNA plus mu B dNB, right? There's your hint. What do we write now? Go ahead. Close enough. It will be mu A minus d psi because A has gone down. The DNA is negative, right? The number of moles of A have decreased. So you have to be consistent with the sign convention. Here my d psi is positive plus mu B plus d psi. And if you're confused here as to why did I write minus d psi, you could have written plus d psi. But the thing is, B's thing would have had the opposite sign. So the thing to keep in mind here is that these two will be opposite signs. So once we have this, this means dg is equal to mu B minus mu A d psi. And let's call this, one moment, this was equation number 6. Let's call this as equation number 7. So now we can define a reaction Gibbs energy or reaction Gibbs free energy, which measures how much did the Gibbs free energy of the reaction change. How much did the Gibbs free energy of the net system change with respect to some progress of the reaction? Okay, so this measures change in Gibbs of the system for unit change in progress. And this is kind of abstract. That's what I meant. We are thinking about a chemical reaction in an abstract sense. What is being held constant here? P and T. So what will this be? This will be simply mu B minus mu A, right? So we give this a name. We call it delta G subscript R is equal to mu B minus mu A. And we call this as equation 8. Okay, I'm going to write down equation 8 on the next page and then resume from there. Anyone wants me to wait on this page? Let me know when you approve moving. Okay, go ahead.
That's the subscript R.
Yeah, subscript R. So I will write down this equation again here. We have delta G subscript R, the reaction Gibbs energy, is equal to mu B minus mu A. So if mu B is less than mu A, forward reaction is spontaneous. This is something we mentioned earlier. If mu B is more than mu A, backward reaction is spontaneous. So let's try to understand this delta RG a bit better. Okay. So we have called it as equation number 8. Let's understand delta RG. In order to understand it, we assume ideal behavior. Ideal gas even. So for an ideal gas, today I reminded you of the relation that mu A is equal to mu A naught plus RT ln PA by P naught. And in the denominator, I'm not writing PA naught because it is some reference pressure, right? Reference pressure can be kept the same for A or for B. Mu B is equal to mu B naught plus RT ln PB by P naught. So this is the same as PA naught is equal to PB naught is equal to some reference pressure. Let's call this as equation number 9. Let's put equation 9 in equation 8. Who all here are taking 482? Bunch of you, some of you. That's going to have a lot of math. So over your winter break, I hope you plan to study linear algebra. Eigenvalues and eigenequations. Otherwise, that class is going to be quantum mechanics is really eigenvalues, eigenequations. So if it's way more math than this class. Let's put equation 9 in equation 8. So what do we get? We get delta RG. Let's just write down everything. So mu B naught plus RT ln PB by P naught minus mu A naught minus RT ln PA by P naught. So this RT ln P naught and RT ln P naught will cancel out, right? It's with a plus and a minus sign. So what will be left with? We will be left with mu B naught minus mu A naught plus RT ln PB by PA. Let's call this as equation number 10. So equation 10 is rewritten as delta RG is equal to delta RG naught, where delta RG naught is the difference of chemical potentials, plus RT ln Q. So I'm just like hammering away symbols. It's for a reason, and it will make sense. So it's just to make bookkeeping easy. We don't want to carry lots and lots of different terms. So here delta RG naught is nothing but a short form for mu B naught minus mu A naught. What is the difference of chemical potential of A and B at the reference pressure, right? You are carrying out the reaction at some pressure. Maybe you measured the chemical potential at some other pressure. And they will be different. A and B are not going to probably have the same chemical potential. So it is that difference between them at some reference pressure, while Q, which is of main interest to us today, is defined as PB by PA, and it is known as the reaction quotient. Why is it called reaction quotient? Any ideas? Someone who has not answered? Yeah, go ahead. That's one guess. Someone else had a guess? Alex, you wanted to answer?
I was just going to say that it's what he said, the quotient.
It looks like, but it's yeah, sure. It's dividing two things. So that's fair. But it's a bit more than that. If the reaction has not proceeded at all, so you're right, it's quotient because it's a division. But what does it have to do with the reaction, right? If the reaction has not proceeded at all, if you have only A, what is going to be the value of Q? Why? There is no B. So when there is no B, what is the partial pressure of B? 0. So Q is 0, right? And if the reaction has fully completed and you have removed all A, then what is partial pressure of A? 0. And what is the reaction coefficient then? Infinity, right? So let me summarize this. We'll wait for just a moment. So a reaction quotient is almost like that progress variable we talked about, kind of like that. So when system equal to only A, then PA is equal to not 0, and PB is equal to 0. Therefore, Q is equal to 0. When system is equal to only B, then PA is equal to 0. The partial pressure of A is 0. And PB is not equal to 0. Therefore, Q is equal to infinity. So as the reaction process proceeds, the value of Q changes, right? So I could make a plot for this. And I would say that as the reaction progresses, progress of reaction, and if I wanted to plot Q, what is the starting value of Q? Zero. I heard someone there. That's okay. We start here, right? And as the reaction progresses, it increases, right? I don't know the curve as per which it increases, right? It increases as per some curve. So start of reaction. And this is towards end of reaction. Next class, we will see how to generalize it for not just A going to B, but some general reaction. And there you will simply have powers of the stoichiometric coefficients. You can almost guess. Here you have B in the denominator because yeah, I mean, we will generalize it next time. For now, let's just think about A and B. So any questions? So this is the progress of reaction. However, so what have we shown so far? We have shown that delta reaction G is equal to delta reaction G naught, which is the reference value, plus RT ln Q. What do we expect to happen at equilibrium? Which one of these three things should have a very special value at equilibrium at constant temperature and pressure? Which one?
Q.
Are you sure? How about the first one, the thing on the left-hand side? Yeah, delta G should become 0. So you're correct. As a consequence, Q will also have a special value. But we know that if delta G is negative, the reaction will keep proceeding in this in a certain direction, right? It is only when delta RG is equal to 0, that's when the reaction will stop happening on an average, right? You will have equilibrium. So at equilibrium, this should be equal to 0. And so what you said is not incorrect. Q becomes K, or Q is known as K. So Q, so just to recap here, Q is always defined as the ratio of PB by PA. But if you reach equilibrium and you calculate the partial pressures of B and partial pressures of A, then that value is called K. How do we get K from delta RG naught? We can see that 0 is equal to delta RG naught plus RT ln K. Therefore, RT ln K is equal to minus delta R G naught. So I'm going to recap all of this. I'm going to write on the next page. So if you have not copied, don't worry. I'm just going to rewrite it. So I just said that delta RG is equal to delta RG naught plus RT ln PB by PA, right? And then I introduced a shortcut. I said this is the same as writing delta RG is equal to delta RG naught plus RT ln Q, right? Where what have we done? We have defined Q as the ratio of partial pressures of B and A. On top of that, we say that at equilibrium, the reaction free energy should become zero. There is no benefit in one direction being favored over the other direction, right? That's what equilibrium means. There is no net change happening. Equilibrium does not mean change is not happening. Equilibrium means no net change is happening. When a drug, so my lab studies drug protein equilibrium. You have a pharmaceutical drug, let's say for cancer, it comes and binds to a protein. Equilibrium does not mean that the drug is never leaving the protein. It means that the rate at which it's equal things are happening in both directions. The number of the ratio, there is something you can talk about the ratio of the protein with drug and the protein without drug. And that, what is that ratio? We are talking about ideal gases right now. So that ratio here is partial pressure. Later we will talk about concentration. So at equilibrium, this becomes 0 is equal to delta RG naught plus RT ln K. So K is defined as PB by PA at equilibrium. Finally, we can say therefore minus RT ln K is equal to delta RG naught, or K is equal to e to the power minus delta RG naught by RT, which is the same as PB by PA at equilibrium. Why is this relation, which I'm going to number as equation number 11, so powerful? My claim is this is very powerful. This is very useful. Why? What benefit could this relation have for us as chemists? Any ideas? Go ahead. I could tell how favored reaction is, but even more importantly, if I knew the value of delta RG naught, which is, I have to look up some table for chemical potentials, right? So you go and Wikipedia, you know, what is the chemical potential of A and B at a particular pressure and temperature? If you put in those values over here and you divide by the value of the temperature and the gas constant, you get the value of K. Once you get the value of K, you directly know that, let's say you got something, for example, 0.001. So this means that the partial pressure of B is 0.001 multiplied by A. If it's an equilibrium if it's a two-component system, what else can we say about the partial pressure? Their sum must be equal to the net pressure, right? So we know that at equilibrium, PB by PA at equilibrium is equal to 0.001. And on top of that, we also know PA plus PB is equal to P net. And you know what is the net pressure of the reaction. So you can solve for PA and PB, right? You can calculate. In this case, what does this tell us? If you put in the value of mu A naught and mu B naught, and you got your K is equal to 0.001, what does it tell us? Does the reaction like to go in the forward direction mostly or the backward direction? What do you have mostly in your container, A or B? A, right? B, you have like 0.01%. So the reaction, you started all A. Only a little small amount of A converted to B, and then it stopped. So you reached equilibrium with very, very tiny amounts of B. That's why this K is so important. It tells you how far will you go and then stop. Okay? Any questions about this? And it's nothing but exponential of the chemical potential difference. So it's a bit abstract, but it really is a consequence of our chemical potentials. If mu A naught and mu B naught were the same value, whatever that value is, what would be the value of K? Cosmo, what do you think? I will write it down. If mu A naught equal to mu B naught, K is equal to? Confident? No, you're correct. So the reason why Cosmo is correct, because if mu A naught, why did you guess 1 then? That's very smart. My most likely guess is 0. It's like right in the middle of positive and negative. Interesting. So if mu A naught is equal to mu B naught, let's do it on the next page and let's work through it. So if mu A naught is equal to mu B naught, what is delta R G naught? That is mu B naught minus mu A naught, right? That is equal to 0. So what is K? K is equal to e to the power minus delta R G naught by RT, right? So e to the power minus delta R G naught by RT, that is e to the power 0 is equal to 1. But in general, mu A naught will be different from mu B naught, right? You can go and look it up and you can measure it and then you can calculate what will be the value of K. And for that value of K, you can go and then say how much of A and how much of B. You can't say how much of A and how much of B would you have, but you can talk about the ratio of that partial pressure, right? You need some other constraints on these in order to actually calculate, but you can calculate the relative values, which is typically quite important. So, okay, any questions about this? So let's think about, and we will resume from this part in the next class again. So it's, by the way, it's very likely now, given the speed at which I progress today, that some of December 6 will also be chemical equilibrium. I will start with kinetics partially on December 6. Whenever we finish chemical equilibrium, I will do kinetics, and December 8 will be fully kinetics. Kinetics is not on the exam, chemical equilibrium is. Yeah, these are simple, but kind of confusing things. So let's progress as slowly as we can. So now, so we just talked about a reaction A in equilibrium with B, right? And here we got that the equilibrium constant, or rather the reaction quotient, is PB by PA. And then we had delta RG, the reaction Gibbs energy, reaction Gibbs energy is delta RG naught plus RT ln Q. But now let's think about a generic reaction where 2A plus B is going to 3C plus D. How do we deal with this? Okay, let's make it even more generic. Let's write it in an abstract way. This reaction can be written as 0 going equal to minus 2A minus B plus 3C plus D, right? So, or if you had more components, instead of A, B, C, D, you have 50 different things in your reaction container, you could write it down in a summation form where you have capital J is equal to 1 till K, which is the total number of components. So in this case, K is equal to 4. And here you would have nu J multiplied by J, right? Whatever chemical species you have, right? This is a general way of thinking. Yeah, go ahead. Huh? New. Very famous of late due to coronavirus. So this is new. So we will start from here and we will show that the chemical coefficient for this is, the chemical quotient for this is very similar to this. We just have the stoichiometric powers. Once we do that, we will talk about something called the Le Chatelier principle, which is how do we affect these two with pressure and temperature. And that's the end of chemical equilibrium. We will then move to chemical kinetics. So please send me your presentations by email or by Slack by tomorrow night. And then one of you have to decide, or your whole team can come here and do a joint effort. We will do that Wednesday. Hi.